doesn't seem like it's on. We're going to resume this session, and the next talk is by Anjaneyulu. And as I just learned that myself, it's on a subject that's different than I anticipated, according to what Brent tells me, because his title was made up for him too. On supersonic jet noise sources. I should point out Brent was with us when we did this test, and there was other, yeah, what was it? Yeah, he was there too. Oh, go ahead, Brent.
Good morning, everybody. My name is Brenton Greska, and for those of you I haven't met, I am a PhD student working for Anjaneyulu Krothapalli, and I should be finishing up in the next month or so. As Jack just mentioned, the title was given to me, however, it actually is relevant to some of the work we're doing. This is the first talk that I'm ever actually going to give regarding just supersonic jet noise sources. Usually I do get up and talk about noise reduction. So today, though, my dissertation is focusing on noise reduction. However, in order to have a good noise reduction technique, you have to really understand the sources that you're dealing with. We have a classical sense, and then I'm going to present some of the results that we've come up with based on some of the research in our lab. This work has been supported by the Office of Naval Research under a contract.
First time I see graciously supported.
That's right, graciously supported. You give us a lot of money. Yes. First and foremost, let me get out of the way, we have the classical jet noise sources, and these include mixing noise and 4 additional noise sources. This was concluded by Crichton, who did a review in the early 70s. He looked at results from recent results at that time as well as previous results, and he came to this conclusion. Mixing noise essentially is the same stuff you see in subsonic jets. These are the large scales responsible for the lower frequencies, and the finer scales responsible for the higher frequencies. And I adopted this convention based on work. The paper is written by Tam with his 2 components of the similarity spectrum. However, now getting into these 4 additional noise sources, 2 of them are Mach wave radiation, are numbered here. So you have high frequency short wavelengths here closer to the nozzle exit, and you have these high intensity, highly directional waves that Vishy actually showed this same picture. And you can see them clearly delineated in this picture. This is an ideally expanded supersonic jet, heated. And based on work done by Ortel, you get this convective Mach number here, which he experimentally found, and I'm going to discuss in a minute. You can also mathematically compute that, and then you can actually figure out the direction in which these high-intensity Mach waves are going to travel. So there's some predictability here. And then the remaining 2 noise sources are shock-associated noise, and these essentially are discrete screech tones and broadband shock noise. Due to time constraints, I'm only going to talk about Mach wave radiation today, but we do have results dealing with both screech and shock noise, so we've got a whole lot of information in very little time. Basically, noise theory, in the last 40 years, there really hasn't been a lot of fundamental discoveries. 50 years ago, we got the work of Lighthill, who basically came up with his acoustic analogy that related acoustics to fluid mechanics very elegantly. And through dimensional analysis, he was able to conclude our velocity to the 8th power law. Well, 10 years later, not to be undone, our guest of honor decided to include Mach wave radiation, which was first proposed by Phillips in 1960. And basically, he came to the fact that velocity cubed now is dependent in the peak radiation direction due to the addition of Mach wave radiation. So since then, though, there really hasn't been anything fundamentally that has added to jet noise. This is the backbone of everything we did. So now, Mach wave radiation. It was found that acoustic disturbances move through the shear layer at 3 preferred speeds, and they're given by W prime, which is greater than W, which is greater than W double prime, in a supersonic jet. This was experimentally found by Ortel using a heated shock tube, and then mathematically this was derived by Tam and Hu, as well as Jack and a couple others for some extreme conditions, using the compressible Rayleigh equation. So there was experimental evidence as well as mathematical proof that this existed. And the equations defining these terms are given here in order of speed. And these are Mach numbers based on these 3 speeds. And just to give you an idea of what these look like from the flow visualization done by Ortel, you can actually see you get what appear to be normal shock waves at W prime. You get some what appears to be almost omnidirectional noise due to W, and then W prime is kind of just there. For subsonic jets, you don't get this NC prime because you can actually get a negative value. But I want to point out that for both subsonic and supersonic jets, you can get both these values. However, for a supersonic jet, these top two values have to be greater than 1. And for conventional purposes, this is the standard convective Mach number that we're all used to dealing with. And I'm going to refer to it as an average convective Mach number based on these results. And this one on top is, I'm going to refer to as a maximum convective Mach number. So just to give you an idea, when I start talking about this stuff, this is what I'm talking about. The red-headed stepchild, essentially, of supersonic jet noise that we never talk about is actually eddy convection. We like to get up and say Mach wave radiation and all this other stuff, but we like to neglect eddy convection. And based on work done by Ffowcs Williams, the equation is actually in your program. It's on the second to last page. And that brutal equation can be simplified by making a number of assumptions, single plane, isotropic turbulence at a far distance, things like that. Essentially, you get this denominator, this value in the denominator, which dictates eddy convection. So, and actually, you can solve this part here, set that equal to 0, and that actually gives you the direction in which Mach wave radiation comes at. Now, if you simply plot this equation, and this was all done 40 years ago, what you see is as you go to higher values of Mach number values, you see the shift in the radiation angle, but you also see, you start to see a decrease. And it was concluded that this was because the eddies that are moving through the shear layer now are moving too fast. So they're not staying in the source generation region long enough. So basically, the faster you go, you're actually going to start losing noise from eddy convection. And that's just something to think about when I talk about the results I'm going to present. So we did experiments in our facility. We did a lot of ideally expanded experiments, a lot of shock noise experiments. We built this nice facility, so we figured we might as well run as many tests as we can. This is the layout of the facility. We sit in the control room during experiments. Everything is computer controlled. Essentially, we have what's called the burner room. This houses the heart and soul of our facility. It's a blowdown facility. We pipe in air from the outside. We have a valving system. Runs into the sudden expansion burner where ethylene is dumped in at the point of expansion. So now we've got air, we've got fuel, we've got a spark plug. Essentially, we've got fire. We can heat the air, so we can get high temperature, high pressure airflows, which you need to accurately simulate the jet exhaust from a jet engine. This fires down into the anechoic chamber. We have a number of nozzles that we can switch in and out, and then it fires across the room, exhausts through a duct, and we actually have a microphone array set up in here. We have a set of rails put up. We can do 1 degree increments, and it's set to within, I think, 0.1 degree of accuracy. So it's actually very well set up. Just a real quick overview. We can run temperatures anywhere between ambient and 1400 Kelvin, which is 2000 degrees Fahrenheit. It's a little hotter than what you see with propane burners, but it's also a little more dangerous, but that's okay. We can run Mach numbers anywhere between 0.5 and 2.5. In the high temperature anechoic chamber, you can actually see the dimensions here. To note, it is fully anechoic to 500 hertz. And the foam wedges are the standard wedges used in this case. They're good to 900, or they're actually fiberglass. They're good to 900 degrees Fahrenheit. So something else that I got to mention, Vichy has addressed this problem in the paper in JFM, is that we do have rig noise in our facility, though. This is a standard directivity plot, and then this is a spectra representing both 90 degrees in the peak radiation direction. What is rig noise? Rig noise comes about due to combustion in the flow as well as valve noise, any bends that you may have, any points of expansion. And what it tends to do is it tends to raise up your lower values greater than what they should be. And what you see is at 90 degrees, you see a lot of increase. This is actually going to affect some of the results that I show you. However, in the peak radiation direction, it's only responsible for this little bubble here, and that only contributes about 0.1 dB to the overall value. So it's, for the most part, it's negligible in the peak direction, but at 90 degrees, it actually causes tremendous differences in the results. It can actually add up to 5 dB to your noise, which actually will shift where your noise dependence, whether or not your velocity is the 8th power or possibly something lower. So, but that's important to note that we do have that problem, and we are working in the process of fixing it, but it's there for all the results I'm going to show. Well, we've got this nice facility. The first thing we did is what happens when you heat a jet. This is actually results, these are results taken from a former PhD student, David Bouchard. It's an ideally expanded jet, and on the left you see this is a cold jet. On the right it's a hot jet, and you can actually see the differences in the Mach waves essentially that are coming off the jet. These appear to be almost Ffowcs. Here they look more like normal ballistic shocks. The velocity is 50% greater when it's hotter. Based on the prediction value for the angle at which the Mach waves radiate, you see you get very close agreement. between both calculated and the value taken from the picture. So instantly, so you also get your shear layer growth rate changes. You get a number of things that happen when you heat the jet. So basically, the conclusion you can take from this is, why can't you just do cold jet experiments? Well, here's why. And this is why it costs so much money to do these kind of experiments, because you have to obtain these real flow features that are in an actual jet engine. The acoustic effects of heating, well, they're pretty obvious. This is a Mach 2 jet, ideally expanded at a number of temperatures, and you see, first and foremost, there's a dramatic increase in the overall sound pressure level. You also see a shift in the peak radiation direction, and the sideline slope right here actually steepens, and it turns out that happens to be a function of the sound speed between the jet and the ambient medium. First and foremost, so this calls into question the relevance of the fully expanded Mach number for the purposes of acoustic investigation. You can also throw out thrust, because thrust is a very weak function of temperature, and then you have the ratio of the sound speed ratio. So for the talk here, I'm going to focus on peak radiation direction as well as 90 degrees. In the peak radiation direction, we should have both eddy convection as well as Mach wave radiation. At 90 degrees, we should have neither. So that's essentially, I'm going to focus on these two areas and present some of the results that we discovered. It's all going to be ideally expanded, 4 different nozzles, Mach 1.3, 1.5, 1.8, and 2. And so based on that, I took values not only from our facility, but also work done by Tana in the mid-70s and work done by Jack and Larry in the early 90s, and plotted all of them together. I also had, so the IE stands for ideally expanded experiments, SN stands for shock noise. I can use the shock noise values in the peak radiation direction because the shock noise is so much less that it doesn't actually affect the overall sound pressure level in the peak direction, but I obviously can't use them at 90 degrees. I wanted to use them because I wanted a whole lot more points, because I'm trying to understand what's going on here. But you can see when you normalize with the acoustic Mach number, you see a linear trend below a value of 1, which is expected. This has been observed in the past. This is nothing new. As a matter of fact, you get, because this is Tana's data, you get velocity to 7.5 power in the peak radiation direction. However, at 90 degrees, because there's rig noise, this should actually be up around 7.5, but the rig noise has elevated the values to the point that it's actually velocity to 6.5 power. So it has already changed what should be velocity to the 8th power. Now this additional rig noise has elevated these values, and the slope has decreased. So that's obviously a problem. So, but obviously you can see above values of 1, there's no collapse. And I'm looking for a collapse. I want to try and make some rhyme and reason out of all the chaos that is jet noise. So continuing on, the very next, what appeared to be logical to me at least, was to go look at the average convective Mach number, MCC, which we're all used to dealing with. And you see in the peak radiation direction, at a value of about 0.75, they all start to collapse. And also in 90 degrees, you see a similar phenomenon. However, below that, there's a lot of scatter, both peak direction and at 90 degrees. Well, why this sudden collapse at 0.75? Well, if you look at the work done by Papamoshu and Rashko, they basically found that they concluded a value about 0.8. I'm going to make it 0.75 just to agree with my results. There's a lot of discrepancy in there. So, but you get a constant normalized shear layer growth rate above this value of 0.75. Essentially, compressibility has now set in, and the large structures that were moving through the shear layer that were responsible for generating noise are no longer the dominant source. So that's, now you're starting to see changes in the actual flow field that are affecting the noise. So progressing along the same line of thought, now I want to look at the maximum convective Mach number, this MC prime value that I showed you, where it actually had the normal shock waves coming off the jet. How did this affect the noise in both peak direction and 90 degrees? Well, now you're starting to see a better fit. The data is still a bit scattered, but now it's actually a value about 1.25. You see this distinct change in the slope of in the peak direction. At 90 degrees, about 1.25, the data all starts to collapse. So now you're starting to understand the flow physics are starting to dictate to the noise in the jet. However, trying to understand why this value of 1.25. Well, I'm no mathematician, so I have to think in terms in isothermal jets. It makes things easy. Everything goes to 1. And it actually turns out, if you solve for the equation for the average convective Mach number, as well as the maximum convective Mach number,
You find out
the
at
value of MC 0.75, you get this value of MC prime at 1.25. So they're linked in some fashion. So this value 1.25 is linked to this value of 0.75. Still not exactly sure why the 1.25, but that's the way it came out. So I've got a value of 0.75 and a value of 1.25. And I wish I could say there was some sheer genius in how I came up with this, but looking at them, 0.75, 1.25, 1 falls in between. So took the average of both the numbers. And you see in both the peak radiation direction and at 90 degrees, everything collapses. Both for subsonic jets below a value of, in this case, value of 0.75, in the peak radiation direction and at 90 degrees. Everything collapses. And in fact, when you do curve fits to both of these in the peak direction and at 90 degrees, you see in the peak radiation direction, up to a value of 1, it follows the velocity to the 7.5 power. After a value of 1, it follows velocity Q, as predicted by Ffowcs Williams 40 years ago. 90 degrees, things don't work out quite as well because we have a lot of rig noise, not only in my facility, but from Tannis. And you actually follow the same velocity to the 6.5 power up to a value of 0.75, and then it actually falls to the velocity of the 4th power. Now, there's no real significance in these numbers, except for the fact that you're losing power of 2. Now, Vishu's not going to like this, but I'm going to contend that you actually do have dipole sources now after this value of 0.75 at 90 degrees. However, in the peak radiation direction, you're seeing Mach wave radiation after this value of 1. Now, there's still, so I basically now have equations where I can predict the overall sound pressure level in the peak radiation direction, as well as at 90 degrees. However, these seriously need to be cleaned up because there's a lot of rig noise here. So, defining this Ortel convective Mach number, that's simply, like I said, an average of the average and the maximum value, which gives you, it accounts for the effects moving through the shear layer, as well as the effects due to heat. Trying to find some experimental evidence as to why this happens. I did come across a paper in which Papamoshu, with one of his PhD students, continued his earlier investigation and found that for convective Mach numbers, average convective Mach numbers greater than 0.4, the eddy convection is actually moving faster than what it originally was predicted. And he derived an empirical equation, which actually the empirical value comes very close to this ideal value. So here's experimental proof now that this equation is holding true in supersonic jets. And just for, to continue on with this, a lot of us used a full expanded, or a convective velocity of 0.7 times the full expanded velocity. Well, actually you can get this value by simply plugging in here. So there's actually now reason behind doing all these things that we've been doing for so many years. So, and it's all based on this Ortel convective Mach number, which is simply an average between the average and maximum values. So to try and give you an idea of what's going on, I'm focusing on the peak spectra. This is to try and provide a little more insight into what's going on with this particular convective Mach number. And actually, by a twist of fate, Vishy had just spoken about this. So first and foremost, I normalized the peak spectra by simply subtracting out the peak value. The red and blue dots signify hot jets and cold jets. So what you see is for acoustic Mach numbers less than 1, subsonic jets, the spectra collapse. And this corresponds to an Ortel convective Mach number less than a value of 0.75. So in that plot that I showed you, values less than 0.75, you've got subsonic jets and you get a collapse in the spectrum. Essentially, this is all, in this peak direction here, this is all due to eddy convection. Back here, you've got different sorts of mixing noise, but in the peak direction, your responsible noise generator is eddy convection. So now we're past the point of being subsonic according to the acoustic Mach number, so now we look at the average convective Mach number. And the average convective Mach number here peaks out at 0.5. So now we're looking between 0.5 and 0.75, and you actually get Ortel convective Mach numbers between 0.75 and 1. And now what you're seeing is you're seeing the onset of Mach wave radiation being added to the noise spectrum in the peak radiation direction. So here we have simply source convection. Here we have source convection plus Mach wave radiation. And so this is essentially a transition region. So we don't have full-blown Mach wave radiation. It's not like flipping a switch. It's actually starting to, there's an onset here. And continue looking at this. So now we're looking between, so now this value of 0.75 we've got normalized shear layer growth rates. Now we're going to look between 0.75 and 1. So we've got normalized growth rates, but we're not moving supersonic yet through the shear layer. And this gives us a range between 1 and 1.25 on this Ortel convective Mach number. And what you see now is you've got full-blown Mach wave radiation as well as source convection. So they're adding together, and once again, red indicates a hot jet, blue indicates a cold jet, and you get a collapse in the spectrum. So that's essentially what this is telling us, why we get these different peak spectra. Well, we've got these different things going on here. So continuing on the same line of thought, I found in the maximum convective Mach number value of 1.25, so I wanted to look at that here as well. So now I'm looking between 1 and 1.25. So I've got supersonic convective Mach number values. And those correspond to Ortel values between 1.25 and 1.5. And now what you actually start to see is you're starting to see the sources are the eddies are starting to move faster through the shear layer, through the source generation region. So they're actually starting to be extracted from the spectra in the peak direction. So now we're getting Mach wave radiation is becoming the dominant force, as opposed to the eddy convection. And I didn't actually have values for this next one, where the convective Mach number exceeds 1.25. However, Jack had them, and in a review paper done by Professor Krothapalli, co-authored by myself and Dr. Arcari, you actually can extend this out, and you find out that it looks something like this with the open diamonds here. And so now essentially your eddy convection is very weakly adding to the jet noise, and its Mach wave radiation is the dominant factor. So from here on out, you would expect to see spectra like this, and that's the kind of stuff you see in rocket noise and values like that. So basically, in conclusion from all of this, the overall sound pressure level values, which I showed you in the peak direction and at 90 degrees, collapse for this Ortel convective Mach number. More specifically, you get an almost velocity to the 8th power for values less than 1, and it goes to velocity cube values for values greater than 1. But at 90 degrees, because I have so much rig noise, I can't actually get up here and say 6.5 to 4. That's not very realistic. Instead, I'm going to contend that we have an existence of dipoles for Ortel convective Mach numbers greater than 0.75. So, and essentially that's at a point where now we've got this convective, the average convective value is now supersonic. So the spectrum in the peak radiation direction displays a sense of universality with transition regions, with the onset of Mach wave radiation, and then the reduction in source convection. And basically what this all means is it's possible to predict the amplitude of a directivity plot in the peak radiation direction and at 90 degrees. So essentially we're putting ourselves out of a job here, in the sense that we're going to be able to predict noise one day based on a few conditions, a few engine design conditions. We're still going to need to do experiments for noise reduction, so don't worry about that. We can still keep taking money. But this, more specifically, will assist people like Jack who have prediction programs for spectra, because in reality, the noise spectra is more important than the overall value. The overall value is just a bulk property. We want to know what the spectra is, what are these different frequencies. Well, this will actually tell you what levels your spectra should be at. So that essentially is the greater importance of all of this. And just real quick, because Jack did mention that I would show some noise reduction stuff for water injection. This is a maximum case. We ran this in the lab on our 1/10 scale. So this is the F18 condition, the black dot, and the blue dots represent water injection in this case. This is a maximum case. We wanted to see what would be the maximum possible value we could get. So the water injection represents 40% of the mass flux in the main jet. So it's not very practical. But we wanted to know just how much reduction we could possibly get, and you see huge values. We're looking at almost 8 dB drop in the peak direction and about 6 dB at 90 degrees. So there's a lot of room for improvement. Like I said, microjets. Why microjets? High momentum flux with normally a low mass flux. In this case, we want to know what would be the best results. And you can choose either gaseous or aqueous medium. Well, what's the difference between the two? Why choose? Gaseous microjets tend to penetrate deeper into the shear layer. And this becomes important because, like I just mentioned, this Ortel convective Mach number is an average between the average convective Mach number and the maximum value. So that means it's nested pretty deep within the shear layer. So you need to get as deep as you possibly can to start affecting where these structures are that are responsible for this noise. That's why gaseous microjets are nice. Aqueous microjets, on the other hand, are nice because they tend to break down when they enter the shear layer, and they start to create a screening effect because they don't actually evaporate. The water doesn't evaporate. It actually breaks down to a small size, at which point in time it starts to generate a screening effect. And what this tends to do is it tends to give you large reductions in mixing noise in both the peak direction and at 90 degrees. And because shock noise is a result of turbulence interacting with the shock cells in the jet, this reduction due to this screening effect basically gets rid of shock noise as well. Because this is a water injection, we do get better results in the peak direction where Mach wave radiation is dominant. So if we had gaseous microjets, we'd actually get better value here. And we're actually working on ways to hybridize the two, where we get the benefits of gaseous injection so we can penetrate deeply, but we also want the benefits of water where we get the screening effect. So that being said, concludes my talk. Are there any questions?
Since you didn't talk about what I thought you were going to, let me just make one comment. In the test that was performed at Laker, what you were able to demonstrate with you and yourself was a tremendous reduction in the amount of aqueous solution that you needed. And over a period of time, that progression, I think, to me, was very amazing. I won't mention what the number is, but it was very, very good. All right, now, question.
There's a profound discrepancy between Oertel's result and your own results. It cannot be a surprise because Oertel made a two-dimensional test.
Yes.
Oertel's test was two-dimensional.
Mm-hmm.
And
You made measurements on a circular jet.
Yes.
And the circular jet has a different phase speed of the disturbances. So the phase speed in a circular jet is dependent on frequency or Stroll number. It's dependent on azimuthal mode number. It is in addition to the ratio of the acoustical of the sound speeds in the inside and outside the jet.
Mm-hmm.
So I'm not surprised that you found this discrepancies. I think it's very well agreement with the results of instability theory.
Mm-hmm.
And at high frequencies, you get values with instability theory up to 0.8 times the jet speed in the isothermal jet.
All right, is there any other questions? If not, thank you, Brent. Oh, you have one back here?
Coming to the water injection and the gas injection,
Yes.
what are the velocities you are selecting?
For the injection,
Yes.
or the injection is actually based on pressure. We look more in terms of the momentum ratio. Then we've got relatively high pressures. We can do up to 1,000 psi gauge. For the most part, the plot that I showed you, that was at 400 psi. So your velocities are dependent upon that.
So what's the momentum ratio?
That's actually a very good question. For that one, I can't honestly answer right now. They tend to be on the order of about 10.